At first, we defined multiplication as repeated addition. We said that A times B means A added to itself B times. In other words, A times B is A plus A plus A plus A plus A plus A, B times. And multiplication makes it much less tedious to compute things like 3 plus 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 3, which is 3 added to itself 10 times, because now we can just write it as 3 times 10, which is 30. Now, what if we have repeated multiplication? For example, if we have 3 times 3, we can compute this to just be 9. And if we have 3 times 3 times 3, well, 3 times 3 is 9, times 3 again is 27. And if we have 3 times 3 times 3 times 3, well, we know that the first 3's multiplied together are 27, and multiplying by 3 again gives 81. But what if we have 3 times 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 3, 3 multiplied by itself 10 times? Well, just like with repeated addition, this is not hard, but tedious. And like with addition, we invent an operation for repeated multiplication. Repeated multiplication is called exponentiation. And we write it as 3 to the 10. So exponentiation is to multiplication as multiplication is to addition. And for those of you curious, 3 to the 10 is 59,049. In general, what we mean by b to the m is b times b times b times b, m times. We call b the base and m the exponent. It's worth pointing out that our definition only makes sense if m is a positive integer. In other words, m must be a natural number, 1, 2, 3, 4, and so on. So now that we have defined an exponent, let's explore it. What if we have 4 to the 2, or 4 squared, times 4 to the 3, 4 cubed? Well, 4 squared is 16, and 4 cubed is 64, so we could write this as 16 times 64, which is 1024. But we could have computed this in another way. 4 to the second power times 4 to the third power can be written as 4 times 4, which is 4 multiplied by itself 2 times 4 times 4 times 4, 4 multiplied by itself 3 times. But in total, we have 4 multiplied by itself 2 plus 3, which is 5 times. So we could have written this as 4 to the 5 power, which is 1024. Computing it this way allows us to compute just one exponent at the end. And there's nothing special about 4 here. If we had x to the second power times x to the third power, we could break it up as x times x, which is x squared, times x times x times x, which is x to the third power, and in total have x multiplied by itself 5 times to get x to the fifth power. And in general, for any numbers m and n, x to the m times x to the n is x first multiplied by itself m times for x to the m, then x multiplied by itself n times for x to the n, to have a total of m plus n times. So we get that x to the m times x to the n is x to the m plus n. Let's keep exploring with our exponents. Now that we know what happens with multiplication, what about division? What if we have x to the fifth power divided by x to the third power? Well, x to the fifth power is x multiplied by itself 5 times, and x to the third power is x multiplied by itself 3 times. But we can make some cancellations because x times x times x divided by x times x times x is just going to be 1, and we'll just be left with x times x up top, which is x squared. And in general, for any numbers m and n, x to the m divided by x to the n can be written out as x times x times x times x m times divided by x multiplied by itself n times. and the first n x's up top will cancel with the last n x's down bottom, leaving us with just m minus n x's in the top. So we get that x to the m divided by x to the n is x to the m minus n. But notice, since we are dividing by x to the n, we need to make sure that x to the n is not 0. And the only way that x to the n can be 0 is if x is 0. So this property only holds if x is not 0. Now let's take a closer look at what we learned about x to the m divided by x to the n. But this assumes that m is bigger than n, and we have more x's up top to cancel with the x's down bottom. But what if m is not bigger than n? First, let's look at when m equals n. In other words, the top and bottom have the same exponent. Well, that means we have x to the m divided by x to the m, and any number divided by itself is just 1. But if we want the power rule to hold, then this should be x to the m minus m. And m minus m is just 0, so this should be x to the 0. But remember, exponents are only defined for positive integers so far. 1, 2, 3, 4, and so on. It doesn't make sense yet to have an exponent of 0. So in order to make the power rule hold, we define x to the 0 to be 1. And it's worth pointing out that because this came from division by x, we need to make sure that x is not 0. So notice now that we have exponents defined for positive integers and 0. And now that we understand the case where m equals n, and we have the same exponent up top as down bottom, let's see what happens if m is smaller than n. To get the clearest picture, let's look when m equals 0, which we understand now. So x to the 0 over x to the n, on the one hand, is 1 over x to the n, because we just found that x to the 0 is 1. But on the other hand, if we want the power rule to hold, then this should be x to the 0 minus n. And 0 minus n is negative n, so this should be x to the negative n. But remember, exponents are only defined for positive integers and 0 so far. So in order to make this power rule hold, we define x to the negative n to be 1 over x to the n. So we now have exponents defined for all integers. It's worth pointing out here that we followed the same order of defining exponents as we did inventing numbers. First, we had the natural numbers, the positive integers. Then, we threw in 0, and finally, included the negative numbers. Following this progression, we will later include fractional exponents in our understanding, but we'll hold off on that for now.